What's up? I'm here very early today because later in the day, around 12, I think before 12, I'll be off. So we're talking, I haven't had breakfast yet, but it'll be from 7, maybe to 11 or 11:30. So if you think about that, that'll be around how many hours? 1, 2, 4 hours. Hello Geary, thanks for joining. Pretty quick. It is currently 7:25. Alright, so I should do a Leetcode. I'm gonna do a Leetcode problem, and then after this do some scheduler development. I gotta fix some issues with the localhost.davidshah.me version of the scheduler development workflow, and I gotta write better docs for the development workflow. Alright, let me see. Hello, okay. Ooh, pretty clean. LXML print soup h1 print line break soup dot p all href soup dot find all href l href for L in all href print line break all href. Not bad. Thanks Geary. Hey man, that's awesome. Wait, let me like this. Thanks for the 100 rupees. Appreciate you, Geary. So cool. Okay, more Van Zao easy scraping tutorial. I see. Fair enough, it did look like a scraping tutorial. Now we go, Leetcode. So I want to try maybe either do a try problem or save it and do a graph problem. If I do a try problem now, I might forget it later, so I might do a graph problem now instead. Rules and gates now. I want to choose a blind 75 graph problem. So I'm going to choose course schedule and open that up. Hey buddy, want to stream together? Maybe. I'd have to see. Let's see. We will try this course schedule problem. Course schedule. Hey, hello Zahib, long time no see indeed. I think every time I've started streaming, it's when you've been gone out. And you got a haircut. Yeah, I did. I got a haircut a while ago now, a week ago. So, and it's kind of messy, I won't lie, as soon as I got out of bed. Okay. It seems like winters are back for you again. Yeah, no, I'm just you know how it is. If it's cold in the morning, I'm gonna be wearing like a full-on extreme piece of clothing. Yeah. You know how it is. Alright, let's try this problem. So we're gonna say this is a graph problem. We might use BFS. 7:30 a.m. So starting up with the day. Yeah, it is. It is. So literally, I woke up maybe 30 minutes ago. What happened to the Amazon intern? It's still coming, you know. We're doing I'll be moving to Sydney at the end of this semester. So at the end of this month. Yeah. You know how it is. Okay. So you are given an array prerequisites where prerequisites I is equal to some list AB, indicating wait, you are given an array prerequisites where this AB indicates that you must take course B if you want to take course A. Okay, so it's a prerequisites in the sense that you have to take B before you can take course A. And the prerequisites list is just the number of prerequisites. So the pair 0, 1 indicates that you must take course 1 before you can take course 0. There are total of num courses that you are required to take, labeled from 0 to num courses -1. There are a total of this many courses you're required to take. Okay. Return true if it is possible to finish all courses, otherwise return false. You know, given your prerequisites, can you finish all of these courses? Let me think about this. Num courses means it's always going to be from 0 to that num courses -1. Return true if it's possible to finish all courses. Now my confusion is whether num courses is going to be the index, is just an index, or if it's the actual subjects themselves. Hello Lucas, damn bro, how are you locking in so early? How does it feel to be done with exams? Yeah, so firstly, like, I'm just so happy to be done with exams. Like, it's like literally the best gift ever to not have to do any of it anymore. So now I can just like focus on actually what I want to do, you know, what I'm passionate about. And yeah, you know how it is. But yeah, still grinding Leetcode. Now, I mean, grinding Leetcode, I guess you can say, you know, there's a bit of passion here. There's a bit of passion. And I think it's not that I'm just doing Leetcode for Leetcode or just doing Leetcode for job search. Because this is still kind of a good way to keep my brain sharp in coding. So with that said, let's have a look at these examples. So num courses is 2. Prerequisites is in order to take class 0, you have to take class 1. Cool. So the output here is true because you have to take 1 first and then take 0, right? First take course 1 and then take 0. And then when you have something like this, in order to take course 1, you must take course 0, and in order to take 0, you must take 1, so it's impossible. Okay, impossibilities. All prerequisite pairs are unique. Prerequisite lengths are less than 1,000, and number of courses is 1 to 1,000. Problem is, this still doesn't answer my question on what this prerequisites means. So I'm going to read this. What nums courses means. There are a total of num courses you can take, labeled from 0 to num courses -1. You're given an array prerequisites where prerequisites A, B indicates that you must take course B first if you want to take course A. For example, if the pair 0, 1 indicates, for the pair 0, 1, it indicates that to take 0, you must first take course 1. Return true if you can finish all courses, otherwise return false. I mean, these are the same examples. All pairs prerequisites are unique. You know, my problem with this is, how can you say num courses Why do you have to emphasize labeled from 0 to num courses -1? I guess that just means, okay, that does mean that it has to be between the, you know, these numbers. So num courses almost like asserts what these numbers will be inside here. It just means that num courses, for the numbers between 0 and num courses -1, you're going to have the numbers within the prerequisites. Okay. With that in mind, how would you go about this problem? You can build a graph, I feel. You know, for each of the prerequisites, you can have a pointing line going from 1 to 0, and then you build out this tree, and then once you build out this tree, or graph I should say, you can try and see if at any point in time you get a cycle, you might have a problem. I don't know how that would work exactly, but hello R, by the way, hello. I have an idea, right? You know, maybe my idea is to build out a graph, build out this graph, have it in, it might have cycles, but if it has cycles, it's a prerequisite. All right, so that means you must take course B. So if you had, say, the situation where you had A, B, B, and then you had also A, C, the problem is here then is this A has to have 2 input nodes before you can continue. So as a prerequisite, you need B and you need C. But you can only do that. Hell. I can think of building a graph, but I can think you can have like an array, a store of all the nodes for all the different subjects, which is going to be a O of num courses. Probably not efficient, possibly. Okay, if I looked away from the problem for 1 second, I would have to start over when bro's reading chat. Bruh. Context switching, I guess. I mean, I don't see how we can do this efficiently from what I already currently know. And I don't think that my way of thinking is going to be efficient because I'm going to be building a hash table, or at least an array representation of size O of num courses. That's what I would be doing. And we would have problems with how to actually check the number of courses well, yeah, the problem is we need to return true if it is possible to finish all courses. But if it isn't possible, oh wait, if it's just possible, no, it can be in any order. If it can be in any order, how would you even start going through the list? Would you go backwards or forwards? If it can be in any order, then maybe you do have to already keep track of an O of num courses. And then, if that's the case, then it's going to be pretty difficult. Okay, well, I have a thought. I think that's enough thinking of that problem, because I can't see of any way beyond what, my current way of thinking is. So let's see how it goes just by looking at the solution here. Also, my nails are disgusting. I have zero idea why they become like this. Some chemistry in my body is going awry. Okay. Adjacency list. Okay. How did we do any adjacency list problem in the past? Now I feel like this problem is going to be too... Oh, something about topological sort I've totally forgotten about. Again. Let's have a look.
Hey everyone, welcome back. Let's write some more neat code today. So today let's look at a graph problem actually. It's called course schedule. We're given a total number of courses and these are our nodes and they're labeled from 0 to n-1 basically. So some courses have prerequisites. For example, if you want to take course 0, you have to first take course 1 and that's represented as a pair or as an edge in our graph. So if you want to take course 0, you have to first take course 1. And the only question we want to answer is it possible for us to finish every course? So let's just look at the first example. We're given number of courses are 2, so that means we have one course 0 and another course 1. We know that the prerequisites are like this, meaning that if we want to take course 1, we have to first take course 0, and I'm going to represent it as an edge going outward from 1 into 0. So what do they mean by possible? Let's just run through
That's literally the
each
opposite way of how I was thinking
courses
it.
and see, is it possible to take each one? So for 0, is it possible to take 0? Well, we don't have any outward edges from 0, so that means 0 does not have any prerequisites. So it is possible for us to complete course 0. Then we look at course 1. It has one prerequisite, which is 0. And we know 0 is possible to complete, so once we finish course 0, then we're allowed to take course 1, which has no other prerequisites, right? The only prerequisite was course 0. So therefore, both of these courses are possible to complete, so we can return true. So let's look at an example where it's actually impossible. So we're given n equals 2. That means we have 2 courses.
Okay, well, I think I see the idea. You just have to scan through
2 prerequisites. So 1, 0,
number
and 0,
courses.
1. This one means that if we want to finish course 1, we have to first complete course 0.
You're gonna have a space and time complexity of at least.
The second one means that if we want to finish course
All
0,
of num
we
courses.
have to finish course 1 first. So 1 is a prerequisite of 0. So the problem with this is kind of obvious, right?
Actually, kind of
There's
worst
a
case.
cycle. So if we want to finish course 0, we got to go finish course 1. If we want to finish course 1, we got to finish course 0, and it just goes like that forever. So neither of the courses are possible to finish. So in this case, we return false. So we can actually solve this problem using depth first search. We can also use breadth first search, and I'm going to show you just the depth first search version because I like it better. So given this new example, the first thing you want to do is visualize it. So I'm going to draw a picture. So we're given 5 nodes. So we have 0, 1, 2, 3, 4. That's 5 nodes. We're also given 5 prerequisites. So in this case, we end up having 5 edges, right? From 0 to 1, 0 to 2, 1 to 3, 1 to 4, and 3 to 4. So my goal here is for each of these nodes, I just want to know, right, for each of these classes, can we complete this course or not? And how do we know if a course can be completed? Well, just looking at this picture, it's obvious, right? 0 has a prerequisite of 2, but 2 does not have any prerequisites, which is great. It also has a prerequisite of 1, and 1 has 2
I gotta eat
prerequisites, 3
breakfast.
and
Hold on, give me a
4.
sec. Hello blocks. Alright, so here's what I'll be back. I just need to quickly eat breakfast, then I'll be back to continue this. I have an idea. But yeah, I'll be back. I'll put on some music right now. You're back. Alright. Let me pause this music. Hello, copy multi. Thank you. Alright. Let's have a look. Continue with this problem. Watching.
3 has
Whoops.
one prerequisite of 4, and 4, luckily for us, does not have any prerequisites. So looking at this, it's kind of obvious that we can complete all these courses. So let's do the algorithm to be able to determine that. We see that these are kind of our base cases, right? 2 and 4 don't have any prerequisites. That's useful information, but we don't need a graph to tell us that. We can use a data structure called an adjacency list, and I'm going to call it prerequisite map because the data structure I'm going to use is a hash map to represent this. So for each of our courses, we are going to have a list of all of its prerequisites. So for 0, we know 0 has 2 prerequisites, 1 and 2. And we're going to repeat that for every single course. So for 1, we know that 2 does not have any prerequisites, so we can just put an empty list over here. 4 also does not have any prerequisites, so we get another empty list. So now we're going to run depth first search on every single node. I'm going to do it in the order from 0 to n minus 1. So be starting at 0, so we're going to run depth first search on it, right? How are we going to do the depth first search? Well, we have our prerequisite map, so we're going to do it recursively. We see that it has 2 prerequisites, 1 and 2. So now let's run
1 and
depth
2
first search on the first neighbor 1. So now we look at 1. We see that it has 2 neighbors.
Give it. Let's go back.
Now
Tonight, Ayo, did you look into ZKPs? I didn't. I said I was. Here's what I'll do, right? After I do this Leetcode problem, I'm gonna actually look into it because it is still interesting.
We're gonna run depth first search on every single node. I'm gonna do it in the order from 0 to n minus 1. So be starting at 0, so we're going to run depth first search on it, right? How are we going to do the depth first search? Well, we have our prerequisite map, so we're going to do it recursively. We see that it has 2 prerequisites, 1 and 2. So now let's run depth first search on the first neighbor 1. So now we look at 1. We see that it has 2 neighbors, 3 and 4. So let's recursively run depth first search on its first neighbor 3. So since 3 is a prerequisite of 1, now we want to know if we can complete course 3. So we look at its prerequisites. It only has 1, 4. So now we're going to check its only prerequisite 4. Can we complete course 4? And then we want to look at the prerequisites of course 4, which we know are empty. This is good, right? So now we see that this is empty. So what does that tell us? That tells us course 4 can be completed, which we basically already knew because course 4 has an empty prerequisite list. So I'm just going to put a little check mark here to say that we know course 4 can be completed. And so recursively, we're going to end up going back to our 3.
Yes.
And we see that it only had 1 prerequisite, and we were able to complete that prerequisite 4.
Yeah.
So therefore, 3 is also a course that can be completed.
Right, because 3 is prerequisites.
And so what we can actually do is, from its prerequisite list, we see 4. We can just remove the 4. We know it can be completed.
Oh, shit.
And so I'm representing that by having an empty list here, right? Just an empty list means that it has no prerequisites, therefore it can be completed. So I removed the only prerequisite that 3 had. Then from 3, we can actually go backwards to 1, which we see here. We can kind of get rid of this 3 because we know 3 can be completed. And then from the 3, we're going to end up going to 4 to check again if 4 can be completed because it is a prerequisite of 1. And since we already know 4 can be completed, we can get rid of that as well.
Okay.
So now we know for sure that 1 can also be completed. And now I'm going to go back to 0, which is how we even got to 1 in the first place. And we look at the prerequisites of 0. We see 1 is no longer a prerequisite because we basically know that 1 can be completed. But we still have to look at this 2. So then we're going to go to the last unvisited node in our entire graph,
still.
which is 2. So now we've gotten to the last course 2. We see it's an empty list, right? Therefore, 2 can be completed. It has no neighbors. It has no prerequisites. So I can put a little check mark here. 2 can be completed. And then we can finally go back to our original node, 0, cross out its last prerequisite, which was 2. And now when we look at 0, even 0 has an empty list of prerequisites. Therefore, we know 0 can be completed. So since we were able to complete every single course, that means we can return true. Every course is completable, and the time complexity for this is going to be big O, the number of nodes we have, which is n. I'll use n as that, and I'll use p for the number of prerequisites that we had, because if you notice in this graph, we have to visit every single node, and we have to move along every single edge. And once we get rid of the prerequisites from here, we don't really have to visit a course twice, because once we know it can be completed, we can instantly do that. We don't have to go through its prerequisites twice. So I'm going to show you one last example. This is the example that what we're going to do. How are we actually going to detect this loop? Because we see, so I'm
interesting.
cross this stuff out because
I will say one thing.
Example, but here we see that 0 has a prerequisite.
One thing before he continues is that it's always starting from 0. Now that is an assumption which I didn't think would be right? Actually, let me continue.
1 has a prereq of 2, 2 has a prereq of 3. So this is a loop. We cannot complete these courses, but how can we actually detect this loop? I'm going to show you how really quickly. So to detect a loop, I'm going to use one last data structure, and it's going to be a set. Though I think you could just use an array if you want. I'm going to call it the visit set. And all it's going to contain is the list of courses that we're currently visiting along our depth first search. So let's say we start at 0, then we add 0 to our visit set. We take a look at the prerequisites of 0. We see it has 1 prerequisite. So then we move to 1. So now we visit 1. So we're going to add 1 to our visit set. And we look at the prerequisites of 1. It has 1 prerequisite 2. So then we move to 2. We run depth first search on 2. So to do that, we have to first visit 2. So 2 is also going to be added to our visit set. And lastly, we see 2 has 1 prerequisite of 0. So then we, of course, want to visit 0. And so now we're going to visit 0 twice.
This is just a visited set, yeah?
0 is already in the visit set. Therefore, we detected a loop. Therefore, we have to return false. These courses cannot be completed. So now let's finally look at the code. So the first thing I want to do is create.
Interesting, okay. For sure. However, let's read up on some zero knowledge proof before we continue with that and write the coded solution. Okay, in cryptography, a zero knowledge proof is a protocol with which one party, the prover, can convince another party, the verifier, that some given, the prover, right? Some given statement is true without conveying to the verifier any information beyond the mere fact of the statement's truth. The intuition underlying zero knowledge proof is that it is trivial to prove possession of the relevant information simply by revealing it. Sure. The hard part is to prove this possession without revealing this information or any aspect of it whatsoever. Right. Cool. Let's have a look. So, in light of the fact that one should be able to generate a proof of some statement only when in possession of certain secret information connected to the statement, the verifier, even after having become convinced of the statement's truth, should nonetheless remain unable to prove the statement to further third parties. Okay. So zero-knowledge proof can be interactive, meaning that the prover and verifier exchange messages according to some protocol. Yeah. Or non-interactive, meaning that the verifier is convinced by a single prover message and no other communication is needed. I agree with that. That could be two possible ways. It could be a protocol, or it could be just something that the prover gives to the verifier. And so in the standard model, interacting is required except for trivial proofs of BPP problems. What's BPP problems? Bounded error probabilistic polynomial time. Okay. Is the class of decision problems solvable by probabilistic Turing machines in polynomial time? So, okay, yeah. Sure. So in standard model, interaction is required except for trivial proofs of BPP problems. I don't know exactly why this is the case. We'll understand that maybe there. In the common random string and random oracle models, non-interactive zero-knowledge proof exists, and this can be used to transform certain interactive zero-knowledge proofs into non-interactive ones. Abstract examples, alright, 2 balls and 2 colored friends. Where's Waldo? Okay, and the definition of zero-knowledge proof, practical examples, discrete log of a given value. I mean, discrete log I can understand to an extent. Hamilton cycle of a large graph, I wouldn't know. Variance of zero-knowledge types. Applications, authentication systems, blockchains. I see. And that's the history, zero-knowledge proof protocols. These are examples of protocols. And there's more. Alright, let's see, let's have a look. So, I want to at least see one of the abstract examples. So you want me to answer the question, what do you think ZKP would be applied to or useful for? I mean, it seems like it would be useful for a lot of things, just from the general understanding, being that you don't need to show the cryptographic, you don't need to prove. Actually, let me read an example and I'll get back to that. All right. See if I can even understand some of these. So, the Alibaba cave. Okay, sure. So this is a well-known story presenting the fundamental ideas of zero-knowledge proof, first published in 1990, and others in their page, How to Explain Zero-Knowledge Protocols to Your Children. The two parties in the zero-knowledge proof story are Peggy, as the prover of the statement, and Victor, the verifier of the statement. Okay, so in the story, Peggy has uncovered the second word used to open a magic door in a cave. The cave is shaped like a ring, with the entrance on one side and the magic door blocking the opposite side. Entrance on one side, magic door blocking the other side. Okay. Victor wants to know whether Peggy knows the secret word, but Peggy, being a very private person, does not want to reveal her knowledge, the secret word, to Victor, or to reveal the fact of her knowledge to the world in general. They label the left and right paths from the entrance A and B. Okay, first Victor waits outside the cave as Peggy goes in. Peggy takes either path A or B. Victor is not allowed to see which path she takes. Then Victor enters the cave and shouts the name of the path he wants her to use to return. Either A or B, chosen at random. Providing she really does know the magic word, this is easy. She opens the door if necessary and returns along the desired path. For sure. So however, suppose she doesn't know the word, then she would only be able to return by the named path of Victor. By the named path if Victor were to give the name of the same path by which she has entered. Since Victor would choose A or B at random, she would have a 50% chance of guessing correctly. If they were to repeat this trick many times, say 20 times in a row, her chance of successfully anticipating all of Victor's requests would be reduced to 1 in the 2 to the power of 20. Cool, I see. Thus, if Peggy repeatedly appears at the exit Victor names, then he can conclude that this is extremely probable that Peggy does in fact know the secret word. I see. So one side note with respect to the third-party observers, even if Victor is wearing a hidden camera that records the whole transaction, the only thing that the camera will record is in one case Victor shouting A and Peggy appearing at A, or in the other case Victor shouting B and Peggy appearing at B. A recording of this type would be trivial for any two people to fake, requiring only that Peggy and Victor agree beforehand on the sequence of A and Bs that Victor will shout. Such a recording will certainly never be convincing to anyone but the original participants. Yeah, okay, that makes sense. So that's why you can't prove to third parties because of this fact. Cool. In fact, even a person who was present as an observer at the original experiment should be unconvinced, since Victor and Peggy could have orchestrated the whole experiment from start to finish. Further, if Victor chooses his A's and B's by flipping a coin on camera, this protocol loses its zero knowledge property. The on-camera coin flip would probably be convincing to any person watching the recording later. I agree. So the zero knowledge property. So the zero knowledgeness is the fact that you can't gain any information about whether Peggy actually has that secret, because maybe Victor is also playing along with Peggy. Okay, so the on-camera coin flip would probably be convincing to any person watching the recording later. Thus, although this does not reveal the secret word to Victor, it does make it possible to Victor to convince the world in general that Peggy has that knowledge, counter to Peggy's stated wishes. However, digital cryptography generally flips coins by relying on a pseudo-random number generator, which is akin to a coin with a fixed pattern of heads and tails known only to the coin's owner. If Victor's coin behaved this way, then again it would be possible for Victor and Peggy to have faked the experiment. So using a pseudo-random number generator would not reveal Peggy's knowledge to the world in the same way that using a flipped coin would. Peggy could prove to Victor that she knows the magic word without revealing it to him in a single trial. If both Victor and Peggy go together to the mouth of the cave, Victor can watch Peggy go in through A and come out through B. This would prove with certainty that Peggy knows the magic word, without revealing the magic word to Victor. However, such a proof could be observed by a third party or recorded by Victor, and such a proof would be convincing to anybody. In other words, Peggy could not refute such proof by claiming she colluded with Victor, and she is therefore no longer in control of who is aware of her knowledge. Zero knowledge proof. Gotcha. So my thinking also with this is this is almost similar to the concept of repudiation or non-repudiation. I forgot which one is how it non-repudiation should be the inability to prove that you are the owner of some key, or your inability to prove that this message was sent by a certain person. That's non-repudiation. So zero knowledge proofs, I'm guessing, is similar to non-repudiation in that respect. But this is also interesting as a protocol because it uses experiments, or it uses like probability, and the chances that it is wrong is extremely low, but still possible, which to me is also pretty kind of scary. If that's, say, like the foundation of blockchain technology, nah, it can't be, right? That's not just based on, say, this, but say if it was, I think the off chance where it gets it right by 1 to the 20, I mean 1 divided by 2 to the 20, if that's ever actually the case ever, where someone just fakes getting the correct key, then they're probably the luckiest person in the world. But also, if it's possible, you know, how many people are willing to try it? But also, interesting. I mean, look, I'm talking about this from a very rudimentary level, in the sense that, you know, I don't know exactly how this protocol is implemented for, I don't know, blockchain technology. But yeah, it's interesting. Yeah, I learned the term on Try Hack Me, but Loki forgot what non-repudiation meant. Yeah, I see. Yeah, that's what Vitalik Burin wants to put ETH into, the field of ZKPs. Someone got to lose 100 million in ETH to ZKP error. Yeah, that's what I was thinking, right? So, yeah. But it's good. But there is no that 100% certainty, right? Which is, to me, a bit scary, but like, I guess this is the cost of zero knowledge proof, despite how little of a cost it is. You know what I mean? But it is interesting. So you can't, I guess that's the whole point of zero knowledge proof, where you're not meant to have 100% certainty. Kind of. On at least the prover's knowledge of a key. But yeah, definitely interesting concept. I'm going to remember this. I actually want to reread now this first bit on the zero knowledge proofs. Yeah, we thought ZKPs were 100% certainty. Yeah, I mean, yeah, I still don't fully know if it is or if it isn't. So in cryptography, zero knowledge proof is a protocol in which one party, the prover, can convince another party that some given statement is true, without conveying to the verifier any information beyond the mere fact of the statement's truth. The intuition underlying zero knowledge proofs is that it is trivial to prove possession of the relevant information simply by revealing it. The hard part is to prove this possession without revealing this information or any aspect of it whatsoever. In light of the fact that one should be able to generate a proof of some statement only when in possession of a certain secret information connected to the statement, the verifier, even after having become convinced of the statement's truth, should nonetheless remain unable to prove the statement to further third parties. I understand that now. Zero knowledge proofs can be interactive, meaning that the prover and verifier exchange messages according to some protocol, or non-interactive, meaning that the verifier is convinced by a single prover message and no other communication is needed. Cool. Now the thing is, like, a single prover message makes it not so. This is like a non-interactive way, a single prover message. Imagine like how that could occur, you know. Yeah, thanks for looking into it. I found it interesting. I guess it's used for optimization or just speed of transactions in places like the blockchain. Kind of worth the risk. Really, do you think it's actually speedier? I guess you know, the number of times that you really just need to run this is 20 times. But what is that in comparison to? Say you have, I mean, I'm trying to compare it to cryptographic techniques that can't provide the same zero knowledge proof idea. But the zero knowledge proof, I guess, yeah, it's meant to be a protocol anyway. Yeah. It's good for transactions that absolutely require a middleman. You can entirely eliminate the middleman. Right. To ensure both parties receive their funds or services. So I suppose it's good for transactions that absolutely require a middleman. Even with the middleman, like, I wouldn't say it's necessarily the middleman, because from like the cryptographic subject that I've taken, we basically talk about middleman problems all the time, like man-in-the-middle attacks, and like even those algorithms, or sorry, cryptographic techniques or cryptographic protocols, they also optimize for middleman attacks, or not optimize, but like prevent middleman attacks also. But I feel like, you know, there is a point somewhere there about a middleman, but with an emphasis on probably zero knowledge proofs. Maybe the middleman cannot prove that somebody actually has the key. I mean, that's probably the whole point of zero knowledge proof, that somebody doesn't have the key. But I guess in the middleman of the cryptographic techniques I've learned in the past, they are assuming that the middleman does assume that, you know, there are some keys that are kept by Peggy, or kept by Victor, or kept by Alice and Bob. And those keys could be later used as proof for their communication with each other. At least in, say, the Diffie-Hellman key exchange protocol. There was another protocol as well. But anyway. Okay. I think that's enough for now. Definitely interesting concept. And I wish I could like bookmark. Oh, actually, you know what? I want to write this. Yeah. So zero knowledge proofs. I want to write this in my Obsidian so I keep track of this. All right. So is where the where external third parties cannot verify that a prover has a key. Only the verifier can prove that only the verifier can conduct experiments to prove that the prover has the key. Okay. Something interesting. First person to find an exploit in ZKP is probably going to be a billionaire. Yeah. It would be definitely interesting on a thesis. Honestly, like, this might be like pretty damn interesting to me. Honestly, something that I might even do in my own research project. Like, it could have big implications. I mean, you can also say the same thing about like the first person who solves the discrete log problem in an efficient time can also break the entire internet. And I think because I think what is it? Diffie-Hellman key exchanges basically done everywhere around the internet. I think what is the basis of SSL. So if SSL can be broken efficiently, then we have problems there too. So, however, nobody's broken or proved the to find the discrete to solve the discrete logarithm problem in linear time or in an efficient time. So it's always been exponential. And what is it? There's a discrete logarithm problem, but there is also the factorization problem, which is the problem of RSA. So if someone can also solve the factorization problem, then they can also, well, not solve the factorization, but provide an efficient way to compute the factorization of two primes. Then you can essentially break into most systems that are running SSH with RSA keys. That is the problem. And obviously you'd probably need the public key of that I guess RSA public-private key, and then you'd be able to say if you solve the factorization problem, you'd be able to get the actual two primes which make up this RSA, and then using those two primes you can generate your own private key in order to log in to, say, someone's SSH server. I wonder if people are actually worried about that threat or not. So you bet people are already. Like, the problem that I've heard is that the NSA or the government keeps track of all of the internet that goes through the wires of whatever the NSA is monitoring, and then they keep track of it all. Although it's encrypted, they possibly can. It's a bit of a conspiracy, but it's very possible that they keep track of all the network requests that are encrypted right now. But the thing is, I don't know, when quantum computers come around, right? So that's the thought. When quantum computers come around, they should be able to theoretically break current encryption on what we have like on SSL pretty efficiently, and as a result there is a backlog of encrypted data that the NSA can probably just decrypt in an efficient amount of time using a quantum computer, and then all of our privacy in the past, I don't know, 10 to 20 years or even further back could be leaked, right? So that's the concern, and people do have this type of concern, right? And so that's why we now have like post-quantum cryptographic algorithms. That's why they exist even before having quantum computers realistically doing anything at all right now. Because quantum computers at its current landscape can only specialize in certain types of tasks. I don't know what they are exactly, but you bet it's computing something more efficiently. But yeah, smart to stay ahead of the curve, exactly. So post-quantum algorithms. Now, what if you need a post-quantum algorithm? I think that's something you have to consider. I'm sure there's people that have considered this as well, like a post-quantum algorithm. Who knows? All right. So now we can try do this course schedule problem. We need adjacency lists. We need to, I guess the implementation is kind of the hardest part here. And I want to think of how to implement this in a way that I would do, right? I don't want to necessarily follow Leetcode's way, but we will have a look, okay? So I know you have to use an adjacency list of some kind. It's almost a given that you have to. But could you build not an adjacency list, but nodes? If you do build nodes, is that good or bad? Is it more overhead than it needs to be? I think it is. Okay, so let's create adjacency list. We are cooked. Now we're back to study for real. Yeah. All right, let's see. So adjacency list. We're just going to call it adjacency list for now, because that is what we have. Thing is, I will use possibly a default dict. So from collections, so it's going to be collections default dict of a list. Okay. And let's have a think. So num courses. For all the prerequisites, I guess. For prereq in prereq. Prereq and prerequisites. Now the prereq could be from to. Okay, from ooh. Yeah, I'll just call it from to, I guess. From subject, maybe. From sub j, maybe. I think that'll be to sub. Okay. Now from sub means from the subject to the subject. Yes, so this is going to be the key of the adjacency list dot append to subject, which should be the, yeah. And let's see. Is that the extent of it? Is it? Is it now? Let me think. Because what if you have duplicates? Is there any care for duplicates? Or is that not necessary? Perhaps not. But I guess in the adjacency list, you should also initialize all the num courses. So for num courses, for courses in num courses, so this is going to be range of num courses. You want to add this adjacency, add the course to the adjacency list. So course to the adjacency list by just initializing an empty list, and then we can just get rid of that. Well, actually, adj list is just equal to an empty dictionary. Cool. What else? I think that sets up the adjacency list that we need. We have a visited. We might have a visited list. So keep an eye on that. Again, all we want to do is return true or false. And the only way to do that is if we maybe did a DFS. All right. So def DFS. At some point, we want to return. And we also want to do the DFS from something and then return the result of the DFS. So technically, the DFS should go here. Okay, and so what do we take as input for this DFS, if anything? Which we should take something as input. Maybe that you start from 0, right? Now this was the assumption that we start from 0. And I don't see how that is actually any better. If we start from 0, how can you really assert that you're going to meet all of it? I guess you can start from any value, is the idea. Maybe. Because if you start from any value, it means eventually if it's true, then you would be able to reach every value. You would be able to reach every course. Is that right? Is that the right idea? It's definitely an idea. The only thing is you would need to say like 0, because 0 here, when I remember what he did, it was a prerequisite for you to do 1 and 2. But say that 2 and the 0 were flipped, then it becomes 0 is a prerequisite of 2. Or you need 0 to, start 2. So if you start from 0, 0 is going to return you correctly 0. Right. So that's a problem. because you're kind of only looking at subsets. Unless you do a DFS of the whole thing. No. This is harder than I thought it would be. Because how can you assert 0 is actually going to be where you start from? Because I don't think he's fully explained that to me. Damn. I'm going to have to look at the solutions here, I think. Dang. Alright, fine. Look at the solutions. Guy you can trust as BFS. Yeah, but starting from what? That's my problem. You know what I mean? Starting from what do you BFS? Okay, so looking at his, he's literally going for any of the courses. If the course is not a prerequisite, if there is no prerequisites for that course, or if the prerequisites are already fulfilled. If it's not fulfilled, then you would return false. And then if everything is fine, then you would return true. He's literally going through all of it then, I see. Kahn's algorithm applies here. Start with nodes that don't have prereqs. I see. Yeah, so you're right about Kahn's algorithm does apply, except I don't know Kahn's algorithm either, but I know that it's here. Which to me then I'm thinking, okay, it's probably worth knowing both of these approaches, right? So I was on the right approach, all right. So I will try the Kahn's algorithm as well as this this cycle detection algorithm. All right, so let's try the cycle detection first though, because since we're already on the way. Course. The idea was to return true. And if, let's see, for course in range of num courses, if not DFS, then you would return false. And then the problem becomes how you build this DFS. You build a visited list or a set. If course in visited, then you would return false, because you know this is a cycle. Whoops. And if you would need to at some point add the course to the visited list. And you would also have to do DFS of the courses. So for Adj, for I guess C in ADJ list of course, then you would DFS course, DFS just C. But after this DFS, if DFS, so if DFS is true, so this is the base case. If course ADJ of course is equal to an empty list, return true. If this is true, then you can remove course. From the adjacency list.
If you do that though, I guess you prevent cycles in the beginning, so it's fine.
So it's never going to come back to this specific adjacency list key in the future. As such, you should be able to just remove this from the adjacency list after you've done the for loop through the adjacency list. Right, so if that's the case, what I think is new list is just going equal to this, and then new list dot append course. And then after you've done all that, the new list dot, so the adjacency list of course is going to equal to new list. Now actually you don't want to append it when it's true, you want to append it when it's false, right? Because if it's false, then you want to append, but if it's true, then you don't want to append and check it again. And then if all goes well, you want to do this final check to return new list
is not empty list. Because if it is empty list, I know this is a bit confusing. Let's see, new list is this, means you would return true. If it's not this, then you should return false. Alright. Damn. There's gotta be some problems with this, I think. Okay, hold on, we got something downstairs. I'll be back. Gotta open the door. Okay. So adjacency is not defined. That's fair. Case 2 works, case 1 doesn't. Is that because it's just always returning false? Let's have a run through of this algorithm. So I can assume this is all fine. So we start from 0. I will say though, actually, let's print course. So this is where it falses. It falses on 0. Okay. So if it falses on 0, let's have a look. When in fact it should be true on 0. Course in visited? No. If adjacency course is equal to empty list, you return true. You would add the course, new list for the C and adjacency list course, that's just going to be 1. If 1 is equal to false, that means you would append it onto the new list, add this back to the adjacency list. And then you return the new list is empty list. DFS C is 1 is equal to false. Then you would append C. but that new list should be empty. It is. Oh, does this just not work? Is it that it has to be equal? Possibly. So I think this might be the reason. True, true, false. Alright, now let's have a look why exactly this is the case. We can debug this. So course, print the course. Look. So you print the course and you're printing 3. Oh, right. Because you don't print the course every time. But let's print the course every time. I should just add this as a test case. Zero, 1, true, 2 true. 3 false when it's meant to be true. So how does this look? 1 to 4, 2 to 4. 3 to 1, 3 to 2. And 4 is empty.
Yeah.
Alright, so where is it falsing from, right? Where can you return? When you print a new list, it's true or false. I guess that's the only place. That means this new list isn't empty. That new list isn't empty, you have 1 and 2. Now where's 1 and 2 in there? Well, because you're 3. If you visited them already, keep it visited. But if you visited them already, then you return false. So every time you do the new course, is it not going to be that the visited has to be reset? Or even visited remove here. Let me think. Visited remove, does that make sense? you remove after the fact. Let's see. There we go. There we go. We do remove visited after the fact. Okay. So we solved it using the way that Leetcode talked about it in his video. However, there is also Kahn's algorithm that we got to look into. But I will probably just save this one to history. Not fully efficient algorithm. Yeah, because it fails this problem. 41 out of 54 test cases. Now that means to me, you know, you might definitely just need cross-calls. I mean, Kahns. So the one other thing I wanted to check was, if I copied this solution and put it in here, would it get the same error? No, it doesn't. So there is a bit of inefficiency that I had in mind. Okay, so let's have a quick look here at why this is better before we continue. I see. Could be the yeah, definitely the reassignment of new list. Okay. Right, so I get it how, I guess, if at any point you get false, and you would return false. But every other time it should be true. So I guess that's always true. And that would work. GG DG P undo because I want to copy this. And then P. Right quit. Right quit all git add dot git commit. Okay. So that's one way to do it, but let's have a look at how we can do it the other way. Now Kahn's algorithm. Going to be the interesting one. I wonder how much different that is. Okay. Let's try and understand this. Pop left from a queue, so is this not going to be BFS? So in degree, okay. Why would you need an in degree? And then you have an adjacency list for I in range of num courses, right? Originally, it's a list of lists. And then for the source destination, in degree destination plus equals 1. What does that tell me? It means at the destination, the prerequisite, there is another prerequisite for that specific number. And then you append at the source the destination number. And then from the queue, in degree if is equal to 0, then wait, so if in degree is equal to 0 for the course, then you append that. Yes, you append that onto the queue. I see. And then you pop the left node from the queue and you can increment finish. I see if finish is equal to num courses, then you're happy. For neighbor in adjacency, for neighbor in the adjacency node, for any of those neighbors, in degree neighbor you less And then if equals 0, you'll append that neighbor. Ooh. I can see how that's breadth first. I can definitely see how that is breadth first. And why is this called Kahn's algorithm? What makes it Kahn's? Right, what makes it Kahn's? Let's understand. So, Kahn's algorithm for topological sorting. This is all we need to understand probably. Given a directed acyclic graph. Ooh. It is a directed acyclic graph. Okay, this problem is also a directed acyclic graph, which is DAG. So there is also a Kahn's algorithm way using topological sort. Kahn's algorithm, okay. Now it's a DAG. I guess maybe that's DAG. We can say DAG, directed acyclic. Maybe call it DAG. Okay. Okay. Let's think more. Okay. Now topological sort, right? Topological sorted order of the graph. What makes a topological? Now what is topological sorted meaning? It means probably from the top. Topological sorted order, it is a linear ordering of vertices such that for every directed edge u to v, where vertex v comes before v in the ordering. Yeah, so this is the definition of topological sorted order, which I should say. So remember this definition of topological sort. Now I might call it topological sort. Create a new Oh. Wait. No. What? Doesn't matter. You get the point, I think.
Wait. Okay. All right. Topological sort. Okay. So in this example, vertices and edges. In the above output, each dependent vertex is printed after the vertices it depends upon. So the output is 4, 5, 2, 0, 3, 1. For this, it would be 0, 1, 2, 3, 4. Oh, 0, yeah, 0, 2, 0, 3, 1, 2, 4, or 4, 1, 2. Or yeah, 1, 4, 2, yeah, definitely. Kahn's algorithm for topological sort is a method used to order the vertices of a directed graph in a linear order such that for every directed edge from vertex A to vertex B, A comes before B in this order. The algorithm works by repeatedly finding the vertices with no incoming edges, removing them from the graph, and updating the incoming edges of the remaining vertices. This process continues until all vertices have been ordered. Add all nodes in degree with a queue while the queue is not empty, blah, 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 blah. Okay, so I think I know how to do this. Auxiliary space. Auxiliary space is a good way to mention like space complexity. Alright, so that's pretty good. Maybe let me quickly look here. So Kahn's algorithm, right? If you use Kahn's algorithm, you need an in degree. So I will say maybe I'll create a new page for Kahn's algorithm. Cool, now that's good. An example. Cool. This graph problem is talking about Kahn's algorithm. And we can copy the solution for topological sort.
Alright, this is epic. This is very epic. Epic beyond no ends. This is well written. Let's go. Okay, I want to try rewriting Kahn's algorithm for myself as a final thing. However, let's go to check. Hello world. Appreciate Ryu for joining. Alright. Okay. Let's try this problem one last time. This time using Kahn's algorithm. Okay. We're going to use Kahn's algorithm this time. Alright, let's go. Kahn's algorithm. So, alright, let's do this. Actually, before I even do this, I want to also write in the boilerplate, because this is something new that I'm learning, or at least know of the term that's new. Use Kahn's algorithm for topological sort problems. Alright, now, hashtag topological sort, hashtag Kahn's algorithm. I mean, Kahn's algorithm here is going to be Kahn's algorithm. Okay, cool. And yeah, topological sort problems like this is also going to be like this. Cool. Cool. I'm going to commit all this if that shows up. Yep, okay. Commit. Okay. Let's try this problem one last time with topological sort in mind. So, instead of using hash tables for our adjacency list, we're going to use the list of lists. Alright. Which is very possible as an alternative. Alright. We also need an in-degree list, which is going to equal to 0 for all the num courses. The adjacency list is going to equal to a list of lists indexed by 0. So a list of lists means we're going to have list list of lists. For I guess nothing in num courses or range of num courses. Could I do that? Should I do that? Okay, I think I should. I think that's fine. Okay. Okay. Now, you gotta add all of the prerequisites, courses. So for course prereq in prerequisites, why is that the case? Okay, let me stand for a minute. I haven't stood in a while. I have not stood in a while. Okay, standing. So for course prereq, course, this is adjacency list course. Dot append the prereq and the in degree you can think of like these lists as either outgoing or ingoing, right? In degree course adds 1. So technically we're thinking of these as coming in to the adjacency list. Okay, now we got a queue. From collections import DQ. Go back. Oops, undo. Go back. How do you go back? Yep. Okay. Q equals DQ. Q dot pop left. Q dot append Q dot append for course in num in range of num courses if in degree of course is equal to 0, then you would q dot append the course. All right, now the problem is that you might have no courses within degrees of 0. In which case they all depend on each other, in which case you should return nothing. Or should return false. If, so while Q is not empty. If Q is empty, damn. While Q is not empty. If Q is empty, then do you want to return false, or is that also going to be true as well? Okay, well, it could be the case where the Q doesn't have something. So I will say that you would need to have if Q is equal to empty list, return false. No. Okay. And while Q course equals Q dot pop left. Now adjacency of the course is going to be the list of subjects to which we care about. So for C in, I see, like these are prereqs. I can change this. For prereq in degree of prereq is minus equals 1. In degree of prereq because you're kind of processing this course now. Wait, but prereq is an in degree of... Okay, this is the confusing part. Which comes when? Which comes before which? How did we want to adjust our adjacency list? Such that the prereqs or such that the adjacency list? You want to go down the prereqs, right? No. You want the prereqs. Damn. How do you do this? Think it through. Damn, it's really just is equal to 0. So I did this Hmm. Hmm. For the most part, it's the same. Alright, let's see. Yo. True, false, true. Why is that? What am I missing here? I mean, what is happening? All right. There is also that aspect. Oh. You're in degree of the... Okay. It's in degree of the prereq. Damn. Does that make sense? Okay, sure. I think that does. But damn, that's still intense. And you're telling me that I can remove that and it still work? Yeah, it would. It still would because it's you're using finish as your final checker. Damn. That's well done. That's well done by the people who made this. So I'm going to use this as alacrity solution. GGDG. GGDG. No. GGD. Yeah, DG. Okay. Done. Okay. Cool. We're done with this question. This took like a solid amount of time, like 2 hours. Basically. I mean, no. Because I had breakfast, but it did take an hour and a bit, an hour and a half, possibly. Cool. Done. So, I guess now it's 10 o'clock. The thing is, I could do more. Not Leetcode, but actually, talking about that, I might try and focus on some of the programming that I have to do. That I want to do. W indeed, guy you can trust. We learned a lot actually today with that Kahn's algorithm. You know, we learned about or reviewed about topological sort. Made sure we understood Kahn's algorithm. Make sure we understood that Kahn's algorithm can only be applied to DAGs, right? That this whole problem was V number of courses and E number of prerequisites. And you could do this in BFS and DFS. You can do this multiple ways, right? So very cool. And I'm happy with that. Okay. Now the other problem becomes, yo, how is that? I got a message from Slack saying there's 3,000 something messages I missed. That can't be right. No, that can't be right. Because I don't see any changes. Okay. Have a quick look at something. Hmm. 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 All right. So we can tick off Leetcode. I'm going to try fix this. Different problem now. Let's have a look. Any commits that I got to make? No. Okay. Now I got to think about closing these. There. Close this. I'm gonna drink some water, be right back. Cool. Cool. Let me try Visual Pseudocode. Yeah. Just got to try development. Just got to try development. And we got to make it readable. Make it readable. All right, in the sense that when you go to this, when you go to technology stack, you read this, okay, you do this, you go to the development guide. All right, you read this, contributing, back to development. All right, here you can find the general development instructions for all new contributors. The guide serves as your first proper introduction to this project. Later in this guide, you can find more specific instructions for the front end or back end development. Lastly, make sure you have read the contributing before coming here. Oh, Nafi. So stumbled across Alphabet 150 today. Another alternative to Leetcode 150. Is that because Alphabet, because Google? Yeah, to prepare to predict Google interview questions. Interesting. Interesting. And it's still pretty similar concepts here, hey? Is there a lot more dynamic programming problems in this? I feel like there would be. Definitely something that, you know, I feel like I could even do as well. Not bad, not bad. I mean, this is targeted to Alphabet. I mean, this is targeted to Google, you know? It's definitely interesting. Gonna keep it on the radar. Gonna keep it on the radar. Okay. Docker compose watch. Okay, Docker daemon isn't running for sure. We're opening up Docker. My CPU is spiked up to 100%. This is building, isn't it? Building from the ground up. Okay. Problem here is that, I mean, now I can go to Docker logs, Docker compose logs backend. See all the backend here. What about front end? What does that look like? Sure. So we got API-localhost. Now I should be able to go to this, but I can't. I don't know if it's because, wait, let me check something. Yeah, localhost is correctly done. I guess dashboard.localhost, API localhost. API localhost. Oh, so API localhost works. That doesn't. That doesn't either. API localhost does. I think that's just a me problem somehow. Let me see. No, that doesn't work. Okay, that doesn't work. But this does. However, this doesn't. Adminer doesn't work. Why? And why is it 404 page not found? So it's just anything becomes page not found. But where is that going to? Yeah, it's any of the C names. I literally just clicked on the correct thing. Okay, well, that's a good question. If you do an asterisk, does that not mean yeah, it's on that server? on that server. It's not on localhost. However, if you do that, does mean that if it doesn't exist there, then you wouldn't be able to okay. No, I can see that. I can understand that. So what about adminer? Adminer has it. You can access the database. But to keep on thinking, I guess you could make everything point to localhost at one point, perhaps. It's something I gotta remember, because it's easily forgettable. Cool.
Oh, the API can't be reached. I think. There we go. All of these errors should be considered. Hmm. No. Okay. API localhost. Localhost. Just trying to think. API localhost, admin a localhost. That wouldn't work, would it? No. But API localhost should. It does. I kind of just need to create like admin a localhost as well. Ooh. It's a record. Oops. Scheduler.
Oh, it's not allowed to be proxied. Fair. Okay, so admin a local host. I should try this again. It should work. DNS points to local or disallowed IP. Because we have API localhost. And that works. And that's only after changing this environment variable. I should also be able to go to traffic. And I want to open these in private windows. Proxy scheduler. Guess you don't know. Localhost 8000, does this actually work? It doesn't. So to me, what does work is API though. Yeah. I don't know why I said it worked. Five one seven three doesn't work, eh? How do I know which ones work, you know, which ones don't? So that works. Adminer. Now it says 8080. But I don't see that loading. And admin localhost doesn't work. I wonder if it's because it just never worked. $80.90. That doesn't work. Why did I say any of this worked? Is this what it's written? Oh, hello. Hello, Discipline. I don't know if you're still here. But I'm working on trying to debug why I can't get any of these links working. And so once I figure that out, I'll be happy with today. But I'll be gone in about 20 minutes from now, just because I have to get ready to go to a meeting. So the rest of the day I'll also be out. So this is going to be ending pretty soon in about 20 minutes. But yeah, right now I'm just trying to figure this out. It's a lot of trial and error, and I wish there was a better way. And I probably feel like there should be a better way than my trial and error. But I digress. Okay. I understand this. Up until this point. Adminer. Adminer, fuck. I can't get adminer to work. Right. Traffic scheduler for sure, that's fine. But okay, that's fine. Could also be ooh. I should be able to log in. Which I can. Okay, I can. So all of this I can reach. Gotta make note of that. Are these clickable links? No, they're not. Yeah, maybe. Maybe I should make them clickable. Okay. Mm. And also same thing, but for redoc. These are all links that work. Right, and then, so those are for the staging. So deployed links. Ideally, what we should have is as one link. Which doesn't work at the moment. So ideally, you know, we would have that working, but I don't know why. Was there something about what was it? Development. Hosts file, I think it was. Etsy hosts. Right. 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 That is a problem.
Okay. Well. Yay! Now that works. Okay, but it's still worth knowing that trick. It's still worth knowing that trick. Okay. Still stumped on adminer. Admin a localhost should work. I'm fine with traffic not having one, neither mail catcher, but adminer. 8080? Really? This is technically still local development, right? Yeah. Is that the case for Fast API?
It is. So maybe that's fine then. So now these all work. These locations, do they work? They do. So they all still work now, I've come to realize. However, why did I change this? Yeah, no, this is fine. This is fine. Bless me. Okay. We figured out that problem. However, now if I just get rid of that and just if it's watch enabled, does that mean if I go this here now? No, it still works. Okay. I'm gonna cancel. Stop watch. If I try opening this, it shouldn't work. So the front end is started. Back end is recreated. Still waiting on the pre-start. Now everything's fine. If I go to this, it doesn't work. If I go to this, it should work. Good. Perfect. Perfect. Now, this does work. These, you don't know if they work until you deploy it, but these do work. That means I need to just double check what we have here. Admin or localhost isn't a necessity. We don't need a wildcard CNAME record. Okay, so this should be fine. Now what? You know, there's an Etsy host trick, right? I guess that's what you want to remember. One central place for links, maybe it's not necessary. Like, this is the questions that I end up ruminating over. So my alacrity when I cat Etsy hosts, this is my Etsy hosts file on Mac. If I want to point local host, wait. API localhost. And also localhost. Perhaps. Okay, so that's a consideration. I know this is not necessarily needed there. Okay. That is more documentation added there. Okay. I'm gonna call it a day, guys. We basically figured out the issue regarding the local host because it was just my computer issue. All right. I'm gonna call it a day. I'll see you guys most likely tomorrow, and we'll continue on from there. All right. Peace, guys.